Hello guys, welcome to this video. In this video we will be continuing all our previous explorations about all the functions and developments that we did, and in this video we shall also find out more about the properties and all the different discoveries that we can make about this exact function and the distributions that we are studying. And meanwhile there would be a lot of solved problems as well, so just head forward to the video. We can start over from there. How to set limits in case of a substitution. And by substitution I mean method of substitution, where we usually substitute for one variable, right, in case of substitution. So let us take an example. Suppose I is equal to 2 to 3 2x by 1 plus x square dx. So this is our given definite integral, and if it was an indefinite one we could have done it easily, but we are not really trying to rely on indefinite integration to solve problems of definite integration, like first evaluate the antiderivative and then put back the function, and not like that. So suppose you do not already know about the indefinite integration, and you just know the methods of it and you want to evaluate it directly. So first of all you have to notice that ddx of 1 plus x square is just 2x, right? So obviously a substitution of u equals to 1 plus x square makes sense. Therefore of, and the substitution would be t equals to 1 plus x square, okay? Then d of t would be 2x dx. So up to this part it is quite similar to as of that indefinite integration, but now the fact is that we also have limits in integration, and these limits are for x, right? So it means that the limit for the variable x is 2 to 3, and what that means for the new variable t, that's what we are going to trying to find out, right? So when x equals to 2, we just need to put the value of x to find out the new limit for t. So it would be 1 plus 2 square, or it would be 5. And when x is equals to 3, t would be 1 plus 3 square, or it would be 10, okay? So this means then we have, and remember in case of indefinite integration at the end we used to put back all the values, but in definite integration there is nothing like that, because it basically represents an area, right? So as we go along we are just trying to find the number which represents the definite integral. We do not need to find any function. So this means that the new integral, which previously was something like this, 2 to 3 2x by 1 plus x squared dx, with the new variable of integration and the limits 5 to 10, and 2x dx would be dt, and this should be t, will give you, and the derivative is ln of t, antiderivative of 1 by t, and the limits are from 10 to 5, so it is ln of 10 minus ln of 5, but this would give you ln of 10 by 5, or in other words ln of 2, which is the answer. So the limit changing is a procedure which can be evaluated just by we use equations, and we put the value of the lower limit and the upper limit separately in the new variable to find out what that value corresponds to the new variable. So if you have like the limits as f of x and g of x, and your new variable is like something in the form of that, you just put in the limits value in the new variable in place of x, or whatever your integration variable is, and whatever value you get for the new variable is your corresponding lower limit or upper limit. To illustrate the fact, let us do one more example. So suppose this was our integral that we needed to find, 0 to 1 1 plus x whole cube dx. Now in this integral, one way as always is to expand 1 plus x whole cube as 1 plus x cube plus 3x square plus 3x and then integrate it separately, right? Another way is to make the substitution, y equals to 1 plus x. Obviously this would give me dy equals to dx, but the limits won't be the same, because the limit for y lower would be equal to 1 plus x lower, which is 1 plus 0, which is 1, and similarly the limit for y upper would be 1 plus x upper, and this should be equals to 1 plus 1 equals to 2. Then the new form is I equals to, and the limits would be 1 to 2, and this should just be y cube dy, right? And now we know the antiderivative is y to the power 4 by 4, and it's from 2 to 1, basically 1 to 2. If you put it in the values, you get 2 to the power 4 minus 1 to the power 4 by 4, right? So 16 minus 1, it's 15 by 4, which is our required answer. So see, if we had done it the other way by expanding, it would have been a bit too messy, but in this way we can get the answer directly. So definite integration is a whole lot easier if you know the properties. And talking about properties, let us do a few properties of it, and we will prove them as well. If a to b f of x dx so a to b f of x dx equals to a to b f of a plus b minus x dx. This is a property, so let us prove it. Now to prove this kind of a property, we need to understand that this looks like f of x becomes f of a plus b minus x, which is not true, but it is true when they are inside the integral. And this also gives you a rough idea that even if two integrals are equal with the same limits, it does not necessarily mean the function inside them has to be the same. Two different integrals can have the same value, and yet the integrand or the function which you are integrating may be completely different, right? Okay, so how to prove it? First let us denote the integral. That integral be a to b fx dx. Now what we can do is we can make a substitute x equals to a plus b minus y. In this substitution, what we get is dx equals to minus dy, right? And the limits would be something like this. So this would be the lower and the upper limits, and therefore the new integral would be a to b, and now it becomes b to a, and it becomes f of a plus b minus y, and there it becomes minus dy, right? So in other words, it becomes minus b to a f of a plus b minus y dy. Now there are two things that needs to be known in here, which I'm going to say. First of all, remember that a to b fx dx is the same as minus of b to a fx dx. So this can be proved in a very easy way, because you can see that let us assume that g is differentiable and g dash x equals to f of x for all x belongs to a comma b, right? Then a to b f of x dx should be equals to g of b minus g of a, right? Why? Because by fundamental theorem of integral calculus by FTIC. And similarly b to a fx dx should be equals to g of a minus g of b, right? And this proves that so this is one of the proofs, right? Now another property that we'd like to prove is that that definite integral is independent of the variable. Right. So what it means is that a to b f of x dx is the same as a to b f of y dy, and this is also same as a to b f of z dz, because it doesn't necessarily matter what variable's name you are using, because as long as the limits are numbers a to, which are like real numbers a to b and not a function, this function f of x dx or f of y dy or f of z dz, all of them will evaluate to the same thing, right? Because at the end of the day, if f has an antiderivative, it will be given as g of b minus g of a, all of them, because it doesn't necessarily matter what variable name you are using, right? So using these two properties, we have that so remember in the here we were trying to prove this, so I equals to a to b f of a plus b minus phi dy, and it became minus a to b f of a plus b minus phi dy. So we had proved that I equals to minus b to a f of a plus b minus y dy. But then again, as I said, the minus b to a, whenever there is a minus in front of a limit of integration, the limits just get reversed, so it becomes a to b f of a plus b minus y dy. And you know that definite integrals are independent of variables, so it doesn't matter if you put a y or a x or a z here, because it's completely independent. So you can write it as well as f of a plus b minus x dx, and since I was already given as a to b f of x dx, right? So yeah, this is one of the properties, and this property would be used extensively in lot of problems when we will be solving problems actually. But now it's time for doing some more of the properties here. Like, first of all, If f is an even function, it becomes 2 into 0 to a f of x dx, right? And if f is an odd function, then this integral is 0. Now this is a question that that can be answered either using graphs or by using the properties of integrals. So since we are trying to avoid the graph theory right now, because we also need to know how to transformation of graphs work in case of even and odd functions, since we do not know that stuff yet and we haven't learned it yet, we are trying to focus on more on the properties of integrals to find this out, which is our basic goal here. So proof so what does an even function mean? So I'll write it down for both of this. So an even function means that f of x would be equals to f of minus x for all x belongs to the domain of f, where f is a function from like domain to real numbers, let's say. And for odd functions, like this. So there are a lot of examples of even and odd functions, like let me give you some examples. F of x equals to x square, it's an even function because f of x is equals to x square, which is also equals to minus x whole square, which is also equals to f of minus x, right? Whereas f of x equals to x cube is an odd function, since f of x equals to x cube equals to minus of minus x cube equals to minus of minus x whole cube equals to minus of f of minus x. Now the property that we were talking about, let us do it like this for the even part. And in doing so, we are going to learn another property which is like this. If f of x is integrable, and the region is divided as a less than c less than d less than b, then so it doesn't matter in how many regions it is divided, or you can divide it in as many regions as possible. So this integral a to b fx dx can always be written as a sum of integrals, which is a to the next number c fx dx plus c to the next number d fx dx plus d to the next number b fx dx. So basically what I'm trying to say is, if we were to evaluate the integral 0 to 3 x square dx, you can write it as 0 to 1 x square dx plus 1 to 2x squared dx plus 2 to 3x squared dx, like this, right? So in our given problem, what we can do is I equals to minus a to plus a f of x dx, and we can separate it into two parts, which is minus a to 0 f of x dx plus 0 to a f of x dx. Okay, now this part is already there, and we need to prove that this I is twice of this, so we need to prove that this one is also equal to this one. So let us denote by j, and let us evaluate j alone. Minus a to 0 f of x dx. Make the substitution. So we make the substitution y equals to minus x, where dy would be equals to minus dx. This would give us, I'm going to figure out the limits later. Firstly, it would mean that this is equals to f of minus y, and dx would be minus dy. And as far as the limits, y lower should be minus of x lower, which is basically plus a, and y upper should be 0. So this should be like from a to 0. Let's bring the minus in the front, and we have minus a to 0 f of y d of y. So the minus reverses the integration limits, so this one will become 0 to a f of y dy, and since it is independent of the change of integration variables, it will be 0 to a f of x dx. Therefore I is equal to 0 to a f of x dx plus 0 to a f of x dx, which is basically 2 times 0 to a f of x dx, right? So to start off, let us do this integral, which is actually a pretty hard one, and it won't be covered in your normal courses unless you are in college, but still it can be solved when you are in high school. So if you remember, I had talked about this before when starting the integration, that this integral equals pi by 2, and I haven't actually told you how to find that integral, and I told you that there is no indefinite integration for this function sine of x upon x, because that this is just not integrable. So to make things clear, to evaluate this integral, we would need some kind of other method. So one of the known methods is complex analysis, which is basically calculus in the complex plane, but we are obviously not going to do that because that is way out of scope of the syllabus of whatever we are studying here. And another method which we can use is parametrization. So this is a method which we can use to solve our current integral. How does this work? Let us see. So we are basically defining a function f of a, and where a is a real number and a is greater than or equal to 0, that is a is non-negative. The function looks like this. So this is the function, and this f of a, and obviously a is greater than equal to 0, this f of a thing, we actually do not know how to find it, or how does this help with our actual problem, right? Because as you can see, the integrand has rather become more complex than being a less bit complex, but I'll show you exactly how this would help us. So watch this. We can see that f of 0 is defined, and it is defined as 0 to infinity e to the power minus 0x sine of x by x dx equals to 0 to infinity sine of x by x dx. So f of 0, the function, is basically the desired integral which we are trying to find the value of, right? And also notice that this also holds, and why we can interchange the integration and the limit is something I would like to discuss later, but for now understand that this is possible. And what we see here is this expression right here. Now you know that a is non-negative, and we have eliminated the case for a equals to 0, and we are tending a to infinity here, and x is always positive. So right, this holds, and since this holds, what we can conclude is this: equals to 0. So our two results are, firstly, f of 0 here is equals to the integral we are trying to find the value of, and limit a tends to infinity, f of a is basically equal to 0, and this is basically due to the uniform convergence of the integral, but that we shall discuss later. So this would, anyways, this problem will be done in two parts, so we shall look forward to the next part where we shall prove some of the identities that I'm going to use. But for this part, let us focus on how to define the function f of a completely and how to make use of it. So recall again the function f a, because once we are done with the special values that we are finding, we need to work with the actual function, and we need to find some way to evaluate it. Because clearly, if I have defined a function which is not really matching to the actual integrand, but in some ways the value 0 gives you back the desired integral, so there is something that we can do with this function to get the value of the integral, right? So what we can do is we can differentiate both sides with respect to a. So it's very important that we are differentiating with respect to a, where a is a variable, and by Leibniz rule of differentiation, under the integral sign you would get something like this. And I would state Leibniz rule of differentiation here after I write this thing. So this basically becomes minus 0 to infinity e to the power minus x into sine of x by x dx. And Leibniz rule of differentiation basically says that So this is the Leibniz rule of differentiation under the integral sign, and the statement of the thing is, if then what happens is as follows. Suppose you have d dx and you have an integral, that is, you're differentiating the integral with limits of ux to vx, and inside there is a function f of t dt. We do not yet know if f of t dt or the function f of t has something in relation to x. So it might be the case that f is a dual function or function of two variables, three variables, we do not know yet. But what it says is for as follows. So this is basically Leibniz rule of differentiation under the integral sign. So let me just read it out again and may make any doubts clear here. So if u of x and v of x are two functions of x which are differentiable, and if f is integrable and f is continuous at all values which u of x or v of x attains, then if you are trying to differentiate an integral with limits u of x and v of x, and the function you are trying to integrate is f of t, if you differentiate it with respect to x, the answer becomes v dash x, which is the derivative of vx, multiplied by f of vx minus u dash x into f of ux plus u of x into v u of x to v of x, the integral. So the limits remain same, but what you do is you differentiate the function f of t with respect to the variable which we were differentiating the original integral with. That is why this is called a dou sign. It's called dou x instead of ddx, because it's a partial differentiation sign. And in partial differentiation, we treat the function as just the function of the variable which we are differentiating with, and everything else remains constant. So if f of t had some, it's a, let's say it's a function of two variables t and x, then t would remain as a constant, or it would act as a constant here, right? And that is the only way, because when we had differentiated the integral in our result, what we did is dou a of e to the power minus ax sin x by x, and this resulted, because sin x by x is constant, as it does not contain anything of x, anything of a, the differentiation was simply of e to the power minus ax, where a is the variable, and this gave us sin x by x into the extra thing is minus x, which is the constant. The constant comes out and the variable remains, which gave us minus e to the power minus ax sin x. So this is how we did it. Now in the next video we shall continue this problem, and we shall see how to evaluate this integral. Specifically there shouldn't be any x here, sorry, it's only 0 to infinity e to the power minus x sin x and a minus in the front, and that's the derivative of f dash t. We would be trying to evaluate this integral in the next one. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes, where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems in theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.